Okay, so we're going to be going into some exponential and logarithmic integrals today. So by now you should have noticed that every integration rule is directly correlated to the function's differentiation rule. So this should be very easy for you guys because you all know what the derivative of an exponential function is, and you also know what the derivative of a logarithmic function is. So the fact that you memorize this already should make this really easy. So the integral of exponential function, so if u is a differentiable function of x, its integral is itself. The same way that its derivative is itself, its integral is also itself. But you always have to remember to add that plus c on it. And then this is the general exponential rule. This is in case you have an exponent that is not just x. Like, for example, you could have a function up there. You could have like x squared plus 1. You could have 2x. You could have a constant, like anything of that nature. So here you have e to the u times the derivative of the exponent with respect to x. The differential is to the x. The reason we have that is because it has an elimination here, which you can see in the next step. You have e to the u du is equal to e to the u plus c, and you always have to remember to replace your u at the end. So here's the first example. We have 2 e to the x dx. The first thing we're going to want to do is remove that constant. We're going to bring that constant outside the integral sign, which is that constant multiple rule. The next thing we're going to do is just imply that simple exponent rule that we talked about on the last slide. We have this e to the x dx statement here. Okay, so we know what that is by definition. Okay, and then we have to just remember to multiply by 2 in the end. Now, with u substitution, if we have something that looks like this is when we have to use our u substitution. So we're going to let u be the exponent. Okay, so u is a 2x. Then du is 2 with respect to x, which is dx. Now, what I'm going to do is I'm going to rearrange the integral statement. A couple of you guys have done a really good job of this. I think that this is really important for you to be able to see what it is that you are actually doing. So you can visibly see now that du is right here. And I'm going to highlight this with blue. And then you could visually see that the u is right here. And I'm going to highlight that with yellow. So it makes the substitution very easy for you in that next step. So now you have e to the u du, and you can integrate that very easily. So that's going to be equal to e to the u plus c, and then you substitute that u back in. You substitute that u back in. Now, if you check your work, the derivative of e to the 2x is e to the 2x times the derivative of its exponent, which is 2. And they match. So my integrand and the derivative of my final answer match. Okay. The third example is if we're using this sum and difference rule, the same way that you guys have been inherently treating these polynomial functions as individual functions while differentiating and integrating is the same way I want you to keep doing it. So for example, if I had e to the x plus x, and I wanted to integrate it, I can use the sum rule. I could split it up down the middle, right? So that plus sign is telling me that I have two statements, okay? And then what I can do is that simple exponential and that power rule. I have e to the x dx is equal to e to the x, that integral. And then I have the x, the integral of x is x squared times 1/2, okay, or divided by 2. And we always have to remember to put that plus c on the end, okay? Now we're going to jump into the logs. Okay, so the logs are a little more tricky, but I don't think they're that much harder. So we're going to let u be a differential function of x. The integral of 1 over x dx is equal to the natural log of the absolute value of x plus c, which is that simple log rule. So if you ever see 1 over x dx, that's going to be equal to the log function. Going to be equal to the log function. The absolute value is very important here. Okay, they are very important here. If you have a function that you're integrating that cannot be negative at any point in time, so like for example, x squared or like x squared plus 9, right? That function's always going to be positive. You can omit the absolute value signs. That's very important. The reason why we want to make sure that these absolute value functions are positive as always is because next week we're going to learn about another application of the integral, which has to do with something that inherently has to do with direction, has to do with value. So we want to make sure that we're respecting those absolute values. I don't want to give it away because it is pretty exciting. Yeah. So this is the general log rule. So this is the general log rule. We have the derivative of u with respect to x over u with respect to x is equal to 1 over u du. So the big thing here is this dx and then this dx will cancel. Okay, they will cancel. So you really just have du over u. That is equal to the absolute value of the natural log of u. Excuse me. So this should have been a u. I don't know, where's my pointer? I'm over there. Okay. This should be a u. Apologies for that. Okay, plus c. Okay, so this is the fourth example. I have 4 over x dx. This is a log function. I know it doesn't look like it right now, but you can see the 1 over x kind of hiding in there. So I'm going to pull the 4 out. Since this 4 is in the numerator, I know that it's a whole 4. I hope that makes sense. Since it's in the numerator, I know that that's a whole 4. So I can bring that 4 out, and then I'm left with 1 over x dx. Now I know that this is a log function. It's there in the flesh, so I can use my simple log rule. I have to multiply by 4 at the end, and then I have my solution. Now think about this in checking your work. You have 4 natural log of x. So the derivative of natural log of x is 1 over x, and then you just be multiplying by that constant, which is 4. Okay. So now with some u substitution, they can get a little complex. So for example, if I have 2x over x squared, I'm going to let u be that x squared. Now, the reason why I'm letting my denominator be the u is because the form that I want is 1 over u. So I want my ending to look like, I don't know where, I can't see the pen. I want my ending form to look like, let me get out of yellow so I can see. I want it to look like 1 over u. So naturally, this is the part that's in conjunction with where I'm looking, right? So like, I'm going to take that as my u. Now, its derivative is 2x. Now, you can see that its derivative is in the numerator. Okay, so that's exactly what I want. I'm going to rearrange the integral statement so that way I can see the du here, and then I have the 1 over u piece here, and I'm going to do my u substitution. Okay, now I can see my natural log statement visible. I do my general log rule and replace my u. Okay, now what you would do if you were solving this problem, taking the derivative of natural log of x squared, this would be 1 over x squared, because the natural log is 1 over whatever's inside of the bars, okay, times the derivative of what's inside the bars. So you have 2x squared, which is 2x. Okay, now you use this same thing as with the exponential functions. It's a log function with the sum and difference rule. You can split these up. Okay, you can split those up. I don't know why I have a 2x there. Apologies. I'm going to just throw the 2 in there. Woo. There you go. Now it's fixed. Okay. I imply the simple log and power rule. So I know that the integral of 1 over x dx is the natural log of the absolute value of x plus x squared. So the integral of 2x is x squared. And then I always add on my plus c. Okay. Please feel free to reach out to me with any questions, comments, concerns. I hope y'all have a great day, and I hope to see you in the calculus chat tomorrow.